Hello students, imagine if we take a simple hydrocarbon and replace just one hydrogen atom with a halogen, say chlorine or bromine. That's how we create haloalkanes and haloarenes. In haloalkanes, the halogen is attached to a carbon with sp3 hybridization, like in an alkyl group. In haloarenes, the halogen is attached to a carbon with sp2 hybridization in an aromatic ring. And Lt, break time is equal to 0.5 S and Gt. Examples are all around us. Chloroform, carbon tetrachloride, even medicines like chloramphenicol, which is used against typhoid fever. Our own body makes thyroxine, an iodine-containing hormone, and its deficiency causes goiter. And Lt, break time is equal to 0.5 S and Gt. For instance, ethane reacts with chlorine gas in presence of light to form chlorothane. Written as C2H6 plus Cl to give C2H5Cl plus HCl, isn't it amazing how a single substitution transforms a hydrocarbon into something so useful? Now, let's classify these compounds by the number of halogen atoms they contain. If there is one halogen atom, we call it a monohalocompound. If there are two, it becomes a dihalocompound, 3 makes it a trihalocompound, and 4 or more makes it a polyhalogen compound. And Lt, break time is equal to 0.5 S and Gt. Take dichloromethane, written as CH to Cl2, a dihalogene compound. Or carbon tetrachloride, written as CCl4, a polyhalogen compound. And Lt, break time is equal to 0.5 S and Gt. And here's an exam favorite. The halogene derivatives can be geminal or vicinal. Geminal means both halogens are on the same carbon atom. Vicinal means the halogens are on adjacent carbon atoms. This tiny structural difference changes their chemical behavior completely, and that's why examiners love asking it. Next are compounds with the halogen bonded to an sp3 hybridized carbon atom. These are haloalkanes, also called alkyl halides. Their general formula is C sub n H sub to n plus 1x, and Lt, break time is equal to 0.5 S and Gt. They are further classified into primary, secondary, and tertiary, depending on which type of carbon atom is carrying the halogen. For example, CH3CH to Cl is a primary alkyl halide. CH3 to CHCl is secondary, also called isopropyl chloride. And CH3 3CCl is tertiary, also called tert-butyl chloride. And Lt, break time is equal to 0.5 S and Gt. If the halogen is attached to a carbon next to a double bond, like in CH to double bond CH-CH to Cl, that's allyl chloride, and allylic halide. If the halogen is on a carbon attached directly to a benzene ring, like C6H5CH to Cl, that's benzyl chloride, a benzylic halide. And Lt, break time is equal to 0.5 S and Gt. Keep in mind this reactivity order: benzylic greater than allylic greater than tertiary greater than secondary greater than primary greater than vinylic. Now let's talk about compounds where the halogen is attached to an sp2 hybridized carbon. First, vinylic halides, where the halogen is directly attached to a carbon in a double bond. A classic example is vinyl chloride, written as CH to double bond CHCl. It is the monomer used to make PVC plastic. And Lt, break time is equal to 0.5 S and Gt. Second, aryl halides, where the halogen is attached directly to a benzene ring. For example, chlorobenzene, written as C6H5Cl, and Lt, break time is equal to 0.5 S and Gt. These compounds are less reactive in substitution reactions because of resonance. In chlorobenzene, the lone pair of electrons on chlorine overlaps with the pi system of the benzene ring, giving the C-Cl bond partial double bond character. This resonance stabilization explains why aryl halides are resistant to nucleophilic substitution. Let's classify the given compound CH2 equals CH single bond CH to Cl into its correct categories. Step 1. The carbon attached to chlorine is sp3 hybridized. This tells us that the carbon forms 4 sigma bonds, including one with chlorine. Step 2. This carbon is part of an allylic system. That means it's adjacent to AC equals C double bond, which will influence its reactivity. Step 3. This makes CH2 equals CH single bond CH to Cl an allylic halide. Step 4. Now, let's look at its reactivity in an SN1 substitution reaction. The reaction proceeds as CH2 equals CH single bond CH to Cl plus H2O, CH2 equals CH single bond CH to OH plus HCl. Let's step into real-life applications. Chloroform, written as CHCl3, and carbon tetrachloride, written as CCl4, are common solvents for nonpolar compounds. Haloalkanes are building blocks for making other organic compounds. In biology, halogenated compounds save lives. Chloramphenicol, a chlorine-containing antibiotic, cures typhoid. Thyroxine, an iodine-containing hormone, regulates metabolism. Synthetic compounds include chloroquine for treating malaria and halothane as an anesthetic used in surgeries. And here's something futuristic. Fluorocarbons, which are compounds of carbon and fluorine, are being tested as artificial blood substitutes because they can carry large amounts of oxygen. So let's sum it up. Haloalkanes and haloarenes can be classified first by the number of halogen atoms, mono, di, tri, or poly. Then by the type of carbon-halogen bond, sp3 carbon halides like alkyl, allylic, and benzylic, and sp2 carbon halides like vinylic and aryl. Whether the halogen is on a primary, secondary, or tertiary carbon changes the compound's reactivity. And we saw that aryl and vinylic halides are less reactive because of resonance and partial double bond character. Beyond theory, these compounds impact our lives as solvents, medicines, anesthetics, and even potential blood substitutes. So remember, classification is not just about labels, it's the foundation for predicting chemical behavior. I hope this class helped you connect formulas like CH to Cl2 and C6H5Cl with the real world around you. See you in the next session for more chemistry adventures.